Our first objective for this lesson is to use the alternating series test to determine whether or not an infinite series converges. So first, let's talk about what an alternating series is. An alternating series is the simplest form of series we can get, where the terms of the series are changing signs. So one term will be positive and one term will be negative, so on and so forth. So for example, if I have the geometric series in here, but notice I have this minus sign written with that 1/2. Rules of exponents say that I can take the exponent of n and just apply it to -1, and then take the exponent of n and apply it to the 1/2 separately. It is this factor of -1 to the n that makes the series alternate. And you'll notice now when we start plugging in terms, our first term is positive, our second term is negative, third term is positive, fourth term is negative, so on and so forth. And so it is the changing of these signs from positive, negative, why we call this an alternating series. So now let's discuss the alternating series test. This test is a test that we will add to our toolbox to help us determine the convergence or divergence in our study of series. So if we have an alternating series, it could have either this form, notice you again see that -1 to the n, or this form. Honestly, it really does not matter what the exponent is on the -1, as long as it's going to make terms positive, then negative, positive, then negative, positive, then negative. So for instance, the exponent could not be 2n, because if the exponent were 2n, then all of the terms would be positive, because -1 to a 2n power is going to be a positive one. So as long as the signs are alternating, then this test can be applied. And the test states that the series converges when two conditions are met. The first is that the limit as n approaches infinity of the sequence that's attached to that series, so there is a sequence going all the way back to 9.1, the limit of that sequence needs to be 0. And additionally, that sequence needs to be decreasing. That means that as the terms increase, they need to be getting smaller for all n values. So this second condition right here, this means that we need to be working with a decreasing sequence. If we can show these two things, that the sequence is decreasing and that it goes to 0, then we can conclude with the alternating series test that the series converges. To be clear, if we cannot show this and this, then we cannot apply this test. It's very important to keep in mind when we're using these series tests, they always have conditions that need to be satisfied. If the conditions are satisfied, then you can reach the conclusion. If the conditions are not satisfied, you cannot use the test at all. It does not mean that you reach the opposite conclusion. It means you need to go use another test. So let's see, and we will see an example where that happens throughout this lecture. So let's look at example 1. First thing is that this does not look like an alternating series. It doesn't have the form of either of these two series that I have boxed in. So first, let's just work on that. I do notice the negative sign on the inside of parentheses with the -2. So we're going to start breaking that apart. Instead of writing it as a -2, I'm going to break it up into a -1 with the same exponent of n minus 1 and then a +2 with the same exponent of n minus 1. So I've just separated those two factors so that I can get closer to seeing this. Now we have a -1 to the n minus 1 in the denominator. That's either going to be a +1 or a -1 as we evaluate the terms of the series. Well, if it's a +1 or a -1, it does not matter if it's in the numerator or if it's in the denominator. So that term that I have highlighted in yellow, I can write it in the numerator instead. And then I would still be left with this n over 2 to the n minus 1. And this is our sequence a sub n. So just matching forms here. Remember I said the exponent on -1 doesn't really matter as long as the terms will alternate, and they will. We'll go even, odd, even, odd. And then everything else that's left in the series is your a sub n, the sequence that you're working with. So for that red sequence a sub n, we need to see if we can show that that sequence goes to 0 and that that sequence is decreasing. So let's go check those two conditions. So checking the first condition, I'm asking, does the limit as n go to infinity of a sub n equal 0? Let's see. So this is the limit as n goes to infinity of n divided by 2 to the n minus 1. We have a theorem that says you can think of that limit as the limit of a function instead of the limit of a series, because when you write it as the limit of a function, you may see the indeterminate form of infinity over infinity, which means that you can come in and apply L'Hopital's rule, which tells us to take the derivative in the numerator to get 1 and the derivative in the denominator to get natural log of 2 multiplied by 2 to the x minus 1. And now that limit clearly goes to 0 because the denominator is the only place where x shows up. So we've shown that the first condition of the alternating series test is satisfied. Let's go check the second condition. I want to know, is it true that a sub n plus 1 is less than or equal to a sub n? We're checking this for all n. And our series starts at 1, so all n is n values that are greater than or equal to 1. So first, let's talk about, well, what is a sub n plus 1? A sub n plus 1 is the nth plus 1 term of the sequence. So not this expression here circled in red, but that expression when you replace n with n plus 1. So I replace the n in the numerator with n plus 1. The n that's in the exponent in the denominator has been replaced with n plus 1. But there's still that minus 1 in there. So this is the expression that we get for a to the n plus 1. And we are checking whether or not it is true that this is less than or equal to a sub n, which is n divided by 2 to the n minus 1. I do not know that this is true yet. This is what we need to show. So I'm going to work with this inequality. I'm going to simplify this inequality and hopefully conclude that this inequality is true, if we can simplify it down to something that is true. So to begin to simplify this inequality, I'm first going to come in and I'm going to multiply both sides by 2 raised to the nth power. And I'm doing that because I want to clear out the fractions. So that denominator of 2 to the n will cancel, leaving me with n plus 1 in the numerator. I'm still checking this. On the right side, let's think carefully about what will cancel here. This fraction that we already have, the n over 2 to the n minus 1, in the denominator, the 2 to the n, the 2 to the n minus 1, I'm going to separate into a 2 to the n multiplied by a 2 to the negative 1. And I can do that because remember, rules of exponents says that you would combine those two by adding the exponents. And if you add the exponents, you'll get exactly that. So it's okay for us to separate and write it like that. And when we do that, it makes it much clearer what will cancel when we multiply by 2 to the n. So we're left with n plus 1. We're still checking, is that less than or equal to n divided by 2 to the negative 1? Well, 2 to the negative 1 in the denominator, we can move up to the numerator with a 2 to the positive 1. And I hope we can see that this inequality is definitely true because n is greater than or equal to 1. So we have shown that the sequence is in fact decreasing. We already said from when we started we knew n was greater than or equal to 1 because of the index on our series. So we've shown that the sequence goes to 0 and that the sequence is decreasing. Therefore, we can now conclude that by the alternating series test, our series converges. In example 2, I am again going to try to use the alternating series test. This is already set up to look like an alternating series. The sequence a sub n is 1 over n. So just as a reminder, I see the -1 with the exponent that will alternate signs. Everything else in the series is a sub n. The two things that we need to check is 1, what is the limit as n goes to infinity of a sub n? Well, when we take the limit as n goes to infinity of this rational expression, 1 over n, that goes to 0 because the degree of the denominator is more than the degree of the numerator. So the first condition of the alternating series test is satisfied. The second condition of the alternating series test is that we need to show that the sequence is decreasing, that a sub n plus 1 is less than or equal to a sub n, that the nth plus 1 term of the sequence, which would be 1 over n plus 1, is smaller than or equal to the nth term of the sequence, 1 over n. And this is absolutely true because recall that a larger denominator means a bigger number. A larger denominator means a smaller number. As you divide by larger and larger numbers, overall the entire fraction gets smaller and smaller. So the two conditions for the alternating series test have been satisfied. Therefore, we can conclude that by the alternating series test, this series converges. Let's look at example 3. Example 3, I do see the -1 to the n plus 1. I'll take everything else in the series and let that be a sub n. Let's see if the alternating series test applies. If I go to check the first condition, the limit as n goes to infinity of a sub n is the limit as n goes to infinity of n plus 1 divided by n. The degrees of the numerator and the denominator are the same, so I'm taking the ratio of the leading coefficients to conclude that this limit is 1, which is not 0. So what that means is that the alternating series test is not applicable. I cannot use it. I can't say that the series converges and I can't say that the series diverges. I'm going to try a new test. And if you run into this when you're testing your series, that's not to indicate that you're not on the right track. This is a part of the process when trying to determine whether or not a series converges or diverges. To be clear, what's highlighted in yellow is absolutely an indication that you should try the alternating series test. It doesn't mean that the test will always work, but you should definitely try it. Once you conclude that the test will not work for this series, if you're starting over with a fresh series that you're trying to test for convergence, the first test you should use would be the nth term test, because that is a very quick way to test for divergence. If you remember, what the nth term test tells us is that if you take the limit as n goes to infinity of everything on the inside of the series, So to be clear, I want to pop back to, I believe, section 9.2, where we learned about the nth term test for divergence. In this theorem, you would take everything on the inside of the series. So this is not set up, formatted like an alternating series. When we learned this, we did not yet know what an alternating series was. So I'm taking everything on the inside of the series. I'm going to take the limit of that. And if that limit is not 0, then I'll quickly be able to say that our series diverges. So let's see what this limit is equal to. To help us calculate this limit, I'm going to split it up into the alternating part, and then I'll multiply that by the limit of everything else, the a sub n. So I took this part and put it inside the first limit, and then I took that part and put it inside the second limit. The second limit is equal to 1. We already talked about that. So this entire limit is just equal to the limit as n approaches infinity of the sequence -1 to the n plus 1. Does that sequence approach 0? It does not. The terms of that sequence go 1, -1, 1, -1. This does not equal 0. So since that limit does not equal 0, the condition of this test is satisfied. The conclusion says that our series must diverge. So our conclusion is that the series diverges by the nth term test for divergence. And yes, I do expect to see your conclusion written. What does the series do? Does it converge or diverge? And how are you reaching that conclusion? Which test are you using? Which test are you using, and what is your conclusion? That is how your answer should look for all of these. Which test are you using, and what is your conclusion? Which test is being used, and what was concluded?